Hello, everyone. So this is the second part of Chapter 11, and we're going to be talking about SN1 reactions, another type of substitution mechanism, and then also elimination. So let me just share here. So an SN1 reaction is a substitution where at the end of the day, you replace a halide with your nucleophile. But the mechanism is different than the SN2. If you recall, the SN2 is the substitution nucleophilic bimolecular, and it involves a concerted mechanism through that trigonal bipyramidal transition state. You get inversion of stereochemistry. This is different because this is stepwise, and the one thing to remember is this one here is unimolecular, and by itself, it's going to lose its halide as a leaving group to form a carbocation. And then in a second step, a nucleophile will come in, react at that electrophilic center to give you your substitution product. We can look at this specifically with this alkyl bromide here. We have a tertiary halide, and the bromide will leave because you're going to form a stable tertiary carbocation. That's the first step. In the second step, a nucleophile, in this case, ethanol, is going to attack with its more electronegative, partially negative oxygen on that electrophilic carbon center. And then you have this H hanging off with the ethanol. So then you do a simple proton transfer. We've done this a lot. Usually it involves water, but same method. The lone pairs of the O and ethanol will come and pick off or deprotonate the H and return the electrons to this O, giving the substitution product here with O-ethyl as your newly substituted group. So overall, what we're having is solvolysis. Solvolysis of your leaving group. This is a process whereby a solvent molecule will come in and attack that newly revealed carbocation center, and your solvent actually functions as the attacking nucleophile. An energy diagram is shown here. Starting with your alkyl bromide, you climb this big hill, that's your rate determining step, to form the carbocation where the leaving group leaves. Then you can have your nucleophilic attack by the solvent, in our case, ethanol. Then a proton transfer to remove this H gives the desired substitution product. So again, forming the carbocation is your rate determining step. You guys have seen this before when we were doing addition reactions of alkenes. So the rate law here is only dependent on the substrate because your rate determining step only involves your substrate. That's why it's SN1, unimolecular. Okay, let's talk about stereochemistry. Could you predict the stereochemical outcome? Let's look at this. This has the stereo center because there are 4 different groups off of this carbon center. Leaving group reveals this carbocation. But remember, carbocations are planar because there are 3 groups and you have this open vacant p orbital that is waiting to receive electron density from a nucleophile. So if a nucleophile comes in an attack, which side will it attack from? Is there a preference? There is no preference. If we look at this example, having the bromide leave gives the carbocation, and the nucleophile has equal probability of attacking from this front side or back side. So what you actually get is if it comes in more from the back side here, I'm just calling this back on this planar carbocation center, it appears as inversion of configuration. So this is kind of like the SN2 in that you get this inversion of configuration, kind of the umbrella flipping inside out. But just remember, it's not SN2. This is not a concerted mechanism. Or the nucleophile can come from the front and you'd get what we call retention of configuration. Basically, the nucleophile just replaces where the halide was, so the configuration here is retained. What we actually see is, we do see roughly 50-50, but you actually do see more of the inversion of configuration. So that means the nucleophile is coming in more from the back side. And the reason is, from the front side, the bromide leaving group might still just be hanging around, blocking entry into that front side. So overall, you see a little bit more inversion, a little less retention. So I said it is still roughly 50-50. Let's look at this. You can do a substitution on this alkyl chloride that has its stereochemistry set. Treat it with sodium hydroxide. You can get a mixture of products. So in this case, you have quite a bit less of this retention and more of the inversion. So how do you account for this? Is the SN1 or SN2 the major pathway in this? So there's a little bit of both going on here. One, there isn't a huge incentive for the chloride to be the leaving group because you form the secondary carbocation, which can happen. So you can have this strong nucleophile come in and just do an SN2 inversion on it. In that case, though, you would have expected 100% of the inversion product, but we don't see that. We actually see only 65%. So here you would have a mix of both the SN1 and SN2 happening. What happened to the chloride ion? It's floating around. It's paired with the sodium. Okay, I'm going to talk about solvent effects and leaving group effects and substrate effects. Solvent effects, we already talked about SN2 reactions like polar aprotic solvents. The reason is polar aprotic solvents for SN2 destabilizes the nucleophile, makes it higher in energy. So then it's closer to the peak. There's less of a hill to climb. SN1 is different because it's a different mechanism. It involves forming a free carbocation. So you have this plus charge in your transition state forming. And so anything that stabilizes this will make the reaction go better. If you have a protic solvent, again, that's something with OHs, something like that, maybe an NH, but definitely an H attached to an electronegative atom. And you can have more of a dipole here, a stronger dipole that can stabilize positive charge. If you could stabilize that carbocation, Hammond's postulate says that stabilizes or lowers the transition state. So in a protic solvent, you can get a lowering of the transition state, a smaller hill to climb. So that'll be better for your SN1 reactions. Let's take a look at this reaction here. So we have this alkyl bromide, this is primary. You have this azide compound, N3, but it's got a minus charge, so it's a very strong nucleophile. So one of the biggest tricks in this section is trying to figure out what is going to happen, what type of SN1 or SN2 reaction will occur, or will an elimination occur? So just focusing on SN1 versus SN2, you got to go back to those tips. Primary carbocations don't like to form. So this does not want to leave. And so this right here, having this substrate as a primary alkyl halide, this azide as a strong nucleophile, this will likely occur through a SN2 reaction. The main reason is for an SN1, you want a stable carbocation, like a tertiary carbocation, or maybe a benzylic or a allylic. So this will proceed in a substitution to give your azide, your alkyl azide, but it will likely be an SN2 mechanism versus SN1. So then which will this be faster in a protic or aprotic solvent? It'll be faster in the aprotic, which is favorable for SN2 reactions. Again, that has to do with destabilizing the nucleophile. So again, for this is SN2, and an aprotic solvent will make it faster versus a protic. Okay, let me just introduce some elimination reactions, and then we'll talk about the similarities between E1 and SN1. So when you have an alkyl halide and you treat it with a base, it can undergo a beta elimination. So an elimination meaning you could deprotonate a hydrogen at the beta position. The halide is on the alpha position. So this forms an alkene. You guys have seen this before in the alkene section. You get your protonated base and then the leaving group as a halide. Eliminations, just like substitutions, can go through either a stepwise or concerted mechanism. So there's actually E1 for unimolecular or E2 for bimolecular. We're going to be talking about E1 today. E1 follows the stepwise mechanism, similar to SN1. So both of those, just remember, E1, SN1, they involve the formation of a carbocation, and the first thing that happens is you leave, your leaving group leaves. So here you could have a tertiary carbocation, and then in our case, our solvent, ethanol, will come deprotonate the H, and then the bond here, the electrons in this bond, will then form a double bond, form your pi bond to give this elimination alkene product. Again, just like SN2, the first step is the rate determining step. That's making it unimolecular, and the rate is only dependent on the concentration of the substrate. Let's look at the energy diagrams for SN1 versus E1. Could you draw this? So you have this first hump, and your first intermediate is your carbocation intermediate. And then for an SN1, you could funnel down to your product, your substitution product. Or if instead you did an elimination, you would form the alkene product. The alkene product is slightly higher in energy because you will have formed a pi bond instead of a sigma bond, and that will be lower in energy. Unless the alkene that you form is very highly substituted, then that can help lower the energy further. The leaving group can have an effect on the rate. Since the rate determining step is for the leaving group to leave, if you have a leaving group that is very stabilized, so these are basically conjugate bases of strong acids. Iodide, I've already shown this. Iodide is a very good leaving group, bromide as well, and then it drops off with chlorine, fluorine the worst. OTS, or the tosyl group, is even more reactive. So if you have an alkyl group, especially if it's a tertiary benzylic or allylic attached to an IBR or a tosyl, those are very reactive. The substrate can make a difference. As I mentioned, tertiary is very good. That drops off with secondary, but that can come into play. So we did see that being operative in a previous problem. Both SN1, SN2 can occur with that. Primary, not so good. So basically, what you need to know is SN1 and E1 mostly observed for tertiary alkyl halides and are too slow for the secondary or primary. But benzylic and allylic are also good. So benzyl group is a carbon attached to a benzene ring. So if you have a plus charge here, you can envision this pi bond moving, like opening the pages of a book, stabilizing that carbocation, delocalizing electron density, or more this positive charge throughout, stabilizing this positive charge by delocalization of electrons throughout the ring. Same thing with allylic. So these three types will undergo solvolysis, and you could get a mixture of SN1 and E1 products. Sometimes you're not going to be able to predict even how much of one's going to occur over the other. For example, this benzylic bromide can be reacted in the presence of water and heat to give first your benzylic carbocation, and then water can come in, add here. So this water can add in proton transfer gives your alcohol product, or water in the presence of heat can deprotonate a hydrogen at the beta position to give the elimination product. What about these two guys? This is not allylic or benzylic. This is vinylic. Because if I removed this halide, the plus charge would literally be on the alkene carbon. If I remove this halide, there's no carbon in between, so it's not benzylic. It'd be on the benzene ring itself, so a phenylcation. Will they undergo solvolysis? No, they don't want to. So I already mentioned the tertiary allylic benzylic, good. Vinyl and phenyl, not good. The reason is hybridization. So the others are sp3 hybridized. This is sp2, and when you remove the halide, you become sp. So the greater the S character is good for stabilizing conjugate bases, if you recall from our acid section, but is not good for stabilizing positive charge. So having greater S character is good for stabilizing negative charge, but it's destabilizing to positive charge. So those don't want to undergo solvolysis. And the primary and secondary alkyl halides will only undergo solvolysis if a rearrangement to a more stable carbocation is possible. So I'll show that here. First of all, I have a secondary. This can actually give a mixture of products. So you could get SN1 product here directly, or you can, you're right, the carbocation that you form here is right next to a tertiary carbon, so you could get a hydride shift to give the plus charge now here, and that can give you the substitution with the water and give you this second product. The other thing you can get is elimination products. So you can see that unless you could really tailor your substrate to give you a specific product, or you can easily separate products, this can kind of be a mess for a chemist to deal with. The polarities of these two are very similar, so it would be challenging to separate. If you use this substrate, which is similar, but it's next to a quaternary carbon, so what can happen is the bromide leaves, you get a secondary carbocation, you can do a methyl shift and substitution to give this product. Or you could have reacted directly on that secondary carbocation to give this guy, or the elimination products. Primary is not so good. And this isn't going to give this free primary carbocation because it's so unstable. So what's interesting is you don't get this huge mixture of products. You actually only get one after a rearrangement, and none of this is observed. The explanation for this is you don't get that free carbocation, and instead the methyl shift occurs at the same time as the bromine leaves. So you're not dealing with that positive charge on that primary carbon, and you only have this carbocation that the water can attack. After proton transfer, you get this alcohol. Okay, so why don't you guys practice? I want you to look at these products, and I want you to draw a mechanism to account for the formation of each. And then also tell me what reagent or reagents you need to complete the reaction. So pause this, take some time, work through this problem, and then I'll go over it. Okay, so here's the mechanism. Look at your substrate. The first thing you want to do is figure out, okay, is this going to be stepwise or concerted? Meaning, is this going to be through an SN2 or E2, which we'll get into later, or is this going to be an SN1 or E1? So basically, you look at your substrate. Do you have something tertiary or benzylic or stabilized by resonance? Yes, you do. So in that case, the halide does want to leave. It's okay leaving because this is a stable carbocation that results benzylic and tertiary. So right there, you should be able to look at a substrate and say, okay, which is going to occur? Then draw that intermediate or just go to the next step. You have your free carbocation. And so now I use methanol because my product has O-methyl as a substitution. So I'm going to use methanol in this case. And so methanol can add in, and then you can undergo a proton transfer, deprotonate that H. This bond goes to a lone pair on O, and you get your SN1 product. So that explains that first product. The second product, and I should have written heat here, generally heat will favor also elimination products. So since you get both, you could do methanol plus heat, just like we've seen water plus heat. Starting with the exact same carbocation intermediate here, I'm just showing a beta hydrogen. And I could deprotonate that hydrogen. These electrons in this bond can come and form a pi bond, and I get my E1 product and the methanol that's protonated. So those are your two mechanisms for forming both of those products. Let's talk about solvent effects. I already mentioned polar product is very good for SN1 and E1. So those have the OHs. These are good because they have the strong dipole that can stabilize and lower the energy of the transition states. The rates are higher. So I don't want to say too much about that, but again, polar product is good for E1 and SN1. I'm going to talk about regioselectivity and stereoselectivity. Regioselectivity has to do with the region of where the new alkene is going to be. So we're talking about eliminations, and basically a substrate could have more than one type of hydrogen to remove. So this substrate has two methyls and this ethyl group. So there are these three different sites that have beta hydrogens to deprotonate to form your double bond. The one that will be preferred is the one that can form the more substituted product. So we call that the Zaitsev product, more substituted. And this is preferred because more substituted alkenes are more stable. We went over that in the alkene section. Less substituted, which we call the Hoffman product, those are less stable. So this will be the preferred major product here. You may also observe some substitution products as well. So if I take this substrate here, heat it with water, and undergo the E1, I have 1, 2, 3 sites. These are the same type of hydrogen, but I have 2 different sites. So you could get a variety of different alkenes. Definitely the more substituted is preferred. So these are preferred. The Zaitsev products are preferred over the Hoffman product, less substituted. This is di-substituted versus tri-substituted. You can get some substitution product as well. This is stereoselectivity, though, that I'm talking about in this slide, which means is a cis or trans or E or Z. The one that's going to form most is the one that has the less steric hindrance, the more stable. So you guys have already covered cis is higher in energy and less stable than a trans, because the trans is less steric, they can get farther away. So if we take this substrate, you have these 2 hydrogens that can be removed. And what we're going to find is to do this sort of elimination, you need to have orbitals aligned. This isn't that crucial to understand this concept, but basically you can rotate these bonds to align the H orbital, the HC orbital, bonding orbital, to align with the empty P. And then do your deprotonation, and then your alkene forms here to give your major product. If you did a bond rotation and remove this hydrogen, then this alkene forms to give the less desired, more, sorry, I think I wrote that wrong. Instead of this being the major, this should be the major here. Let me look at that. No, that's correct. I apologize. Here we have methyl versus methyl here. So there's some sterics here, but the other option would have been ethyl. So this is correct. You want to have the two bulkiest groups trans to each other. Sorry for that. So methyl here, trans as far away as possible from ethyl. And then here, the methyl is cis to the ethyl. So there's more sterics in this situation. So that's why this is not preferred. These are bumping into each other more. And this is preferred because methyl's away from ethyl. Okay. So this just shows the same thing again, and basically just spells out that each hydrogen can be the top or bottom here and undergo the elimination, but that can occur because as long as the orbitals are aligned, those sort of products can be formed. The preferred product will still always be the one that will have the least steric hindrance. Okay, this is the final slide for you guys. So I want you to draw all of the expected products for this solvolysis reaction. So we have this substituted cyclohexane, or this cycloalkyl halide, and you're going to treat it with water and heat. So go ahead and pause and write all the possible products, and I will give the answer. Okay, so since this is tertiary, this would go under a mechanism where you would first have the chlorine leave and generate the carbocation. So both SN1 or E1 can occur here. Water can come and add and give you your substitution product. There's no rearrangement because you already have a good tertiary carbocation. You could get the substitution product. The other thing that can happen is if you have a positive charge here is you can remove a hydrogen from one of these carbons or this carbon. You can do both. If you take one from the outer region, you get this less substituted Hoffman product. It's only disubstituted. But if you pull off and deprotonate a hydrogen from this carbon or this carbon, you can get the internal double bond, internal meaning within the ring, and this is a tri-substituted double bond. Notice that this is obviously a product from removing a hydrogen here, forming a bond here. You can do the same thing here, form your double bond here. I don't redraw it because if you just flip it over, it's the same compound. Okay, so that's it for this section, and we'll continue with chapter 11 next time.